Give them a chant gang, 1, 2, 3, Decca, at the top of our lungs. How many times you get to shout out in school at the top of your lungs, use your outside voice? Want to go ahead and do it, gang? Why not, gang? On 3. All set, cameraman? Cameraman is Kyle No today, manning the cameras. All set, Kyle? Okay, here we go for our DECA state champs. To knock it home today in the final moments. On 3, DECA. 1, 2, 3, DECA! Muy bien, that was good. Way to go, gang. Do we get an A+? I think we get an A+, huh? For shouting out DECA. Okay, gang, let me take the freeze off. Okay, little review from yesterday, and then, so I'm going to go through these slides real quickly with you until we kind of get to where we left off yesterday. So again, really this unit is starting out by talking about, guess what idea? Again, our conceptual chemistry book, again, whole chapter just dealing with this. It's a whole chapter. Chapter 10 in conceptual chemistry, all dealing with guess what idea. What do you be thinking? Let's pop this one out to Tony. King center mass. King center mass, center of gravity. I use those two terms interchangeably with one another. Again, as if they be a meaning of the same exact thing. Although there is a slight difference, again, in this class, we're not going to dwell on it, pound it to death. But just like there's a difference between weight and mass, there is a slight difference between center of mass and center of gravity. But again, center of mass is where you can take an object, again, where old Mother Earth assumes every molecule making up the thing happens to be. So again, for your textbook, we did this last time. Again, right smack dab at the center of the thing. That's where its center of mass is. Again, as far as old Mother Earth is concerned, she pulls down on the textbook as if every particle making it up. Every molecule located right there. Therefore, again, if you want to experimentally determine that, again, what's one way to do it? Again, I'm going to give you a quiz. Again, 2 ways to experimentally determine. Again, as long as the center mass is within the geometrical boundaries of the thing. Again, this way. The other way, it doesn't matter. Again, 2 ways to kind of experimentally determine where that center of mass is. What's one way? Let's pop this up to it. The King of Jordan. Okay, yeah, balancing it, huh? Again, if I let go and it balances. Again, the center mass needs to be within. Again, the area bounded by my fingers. We call that the base of support. And I think we made it to yesterday, again, why that is, why that has to be true. And when we get there again, we will review that again. So again, that's one way to experimentally determine where something's center of mass is. Hey, the other way was to use a guess what. Let's pop this one out to, I'll stop on this one. What say you, let's pop this out to Devin. The good-looking fella up front. I gave a plump out, so we'd be calling that a plump out. Hey, doesn't that look like a plump? So you can suspend it from any 2 different points that you want. They did 3 here. Ba-wump, and ba-wump. Again, where the plumb line intersects. Again, that's where the center of mass of the thing is. Again, if you want to double check that, again, go ahead and put your fingers again at that point. Again, if it balances, that's where its center of mass is. Again, guess where the center of mass of Gus's iPod 7 is. My goodness gracious, that was fancy schmancy. I wish I had the big bucks for an iPod 6. Is that a 6? Wow, iPod 6. Is there anything after 6? Ooh, somebody's got the big bucks. I've got my flip phone. Why don't we do that in front of the camera? We'll do that in front of the camera for folks. Do you mind being on camera? Here we go, Gus is going to show you where the center of mass is of his iPhone 6 is, huh? But there it is, man. That's the big bucks. He's risking it. You don't understand the nerves involved with doing that game. One little slip up, one little mess. He doesn't have it exactly at the right location. Falls, crashola. Again, what is that? $500 for one of those bad boys? Really? I can't believe it. Somebody's got the big bucks. My goodness gracious. Ba-wump. Are they $500? Really? Or $600? Really?
contract.
On contract?
Off contract is like that.
I got enough.
What does that mean off contract?
It's like if you just buy the phone from like a sketchy site and you don't pay anything
sure Gus didn't do that. Oh, very good, upgraded. Goodness gracious. Mrs. Nedobeck wouldn't let me spend $1,000 on a phone. She wouldn't even let me get ESPN to watch the football games. The best I could. GD was on TV a couple days ago playing for NCAA bid. Didn't get the station. No, you can't have. As a matter of fact, our AP just went up by like $9. We got to talk to them. We can't have that. I'm gonna have to cut more stations now. No, I'm gonna go do something else. That's how you always get the better deal. I keep switching. Okay, plumb bob. Defined by the center mass. And again, when we found the center mass of this L-shaped object, again, that brings about a very, very important point. Again, the center mass doesn't have to be guess where. What do you be thinking? Let's pop this one out to F. Yeah, game doesn't have to be where there is mass. Game doesn't have to be where there is stuff. Game doesn't have to be where there is matter. Game, it can be located outside the geometrical boundaries of the thing. So again, gang, the coffee pot, game, the boomerang, again, a donut before he took a bite. Smack dab in the middle where there is no donut. Hey, where's the center mass of a ping pong ball located? What say you? Let's pop this one out to Adam.
In the middle of the ping pong ball?
Yeah, right smack dab in the middle of the ping pong ball where there's no ping pong ball. That hard plastic doesn't even exist there. So center mass doesn't have to be where there is mass. Center mass doesn't have to be where there is stuff. So again, we used yesterday the plumb bob to find out where the center mass of this L-shaped object was. And it was, again, which brings us up to, again, I think, we left off with this slide. Again, it turns out to be about right there-ish. True or false? Let's say, let's pop this out right now. Do you remember? Yeah, gang is not there, huh? Bum womp, gang is more like down there-ish. So gang, here's the idea. To say that that's where the center mass of this object is. Gang, it's to say, as far as old Mother Earth is concerned, gang, she treats this whole object, gang, as if every particle making it up, gang, located right there. Gang, at that particular point in space. And so we kind of modify, gang, what we learned last semester when we would draw an arrow representing the weight of something, and we label it mg. Hey, that's the weight of the thing. Okay, the tail always originates at where the center of mass is. So in this case, again, we would put it there, where there is no mass, where there is no stuff. Again, as far as old Mother Earth is concerned, the whole object is located right there at that red dot. And again, guess what's beneath the red dot? Guess what's underneath the center of mass of this thing? Begins with an N-O. And it's a thing. What say you, Catherine? Okay, there's nothing there. Okay, the last point of support is right there. So again, that force, is going to cause this thing to twist. Again, there's going to be a twisting force acting on this thing. Again, the twisting force by definition is, you take this force and multiply it by a very, very special distance. Again, that very special distance is called the lever arm distance. Turns out, gang, the lever arm distance is the shortest distance, gang, between the line of force. Gang, in other words, we took this line and extended it down indefinitely. Gang, extended it up indefinitely. Gang, the shortest distance between the point about which rotation takes place, gang, which is this point right here. So it's going to rotate about that point as if there's a little fulcrum right there. The shortest distance between that point and this line of force is the lever arm distance. Gang, and I'm showing it to you right there in blue. And that's the lever arm. Sometimes kids say, well, why don't we go from the point about which rotation takes place to the center of mass of the thing? Why don't we take that distance? Because that's not the shortest distance. Again, as a matter of fact, gang, along this line of force, bum womp, okay, there's an infinite number of points. Again, we can go to any point on that line. But again, the shortest distance is always, gang, this orthogonal distance. Getting this transverse distance, this normal distance, getting this 90-degree angle distance, this perpendicular distance. Again, that's always the shortest distance. So again, that distance is called the lever arm. Again, take this force in newtons, which isn't the weight of the thing, multiply by that distance in meters. Again, you're finding out how many blank units of torque acting on the thing. Okay, what's the unit of torque, that being the case? That it is force times lever arm distance. What say you, Zach? Can you read the music? newton meter. Again, we measure torque in newton meters, so many newton meters of torque. Again, acting on this thing, making it twist. Again, making it rotate. So a torque is a fancy way of saying a twisting force. Turns out, again, if something is not rotating, again, when there's a net torque acting on it, it will rotate. Again, just like net forces cause something's linear state of motion to change. Okay, net torques cause the rotational state of motion of something to change. Okay, if something's not moving, exert a net force on it, that will make it change its linear state of motion. Okay, if something's not rotating, exert a net torque on it, that will make it rotate. It turns out, again, just like net forces change the linear state of motion of things, again, net torques will change the rotational state of motion of things. So again, if something's not moving and there's a net force engaging it, again, it's going to start moving. Okay, if something is moving and there's a net force acting on it, maybe it starts moving faster. Maybe it's going to move slower. Again, maybe it's going to go in a circle. Net forces change the linear state of motion of things, just like net torques change the rotational state of motion of things. So again, net torques cause rotational acceleration, just like net forces cause linear acceleration. So again, did we complete this one last time? Did we finish it up? Okay, did we make it to this one now? Well, won't. Okay, let me go through this one just as, let me just put it up there since we did it, we did this one yesterday. Okay, we ended here. Okay, so we kind of did it and ended here. So again, just showing you this now. Again, this is Newton's second law. Again, this is then the rotational equivalent of Newton's second law. Again, the rotational equivalent of little a, linear acceleration, is alpha. Angular acceleration, the rotational equivalent of net force, again, is the net torque. The rotational equivalent of mass, again, we're going to probably spend 3 days just on this. Again, it's rotational mass. Again, rotational inertia. Again, it's the laziness, stubbornness, resistance that all rotating systems have to a change in their rotational state of motion. Okay, gang, we didn't do this one then. Okay, here we go, brand new. Again, here's a refrigerator. Guess what the black dot on the refrigerator be representing? What do you be thinking? Let's pop up to Tori. Okay, that's the center of mass, huh? Again, the center of gravity, CG, Cn. Okay, in other words, old Mother Earth pulls down on this refrigerator as if every molecule making up the refrigerator, every atom making up the refrigerator, okay, located right there at that point in space. So again, that's the force engaging the refrigerator. Okay, what does this force represent that's acting on the refrigerator? What do you be thinking? Let's pop this one out to, let's go with Chase. Yeah, that's the normal force. So again, old Mother Earth is grinding that refrigerator into the floor responds and pushes up with an equal and opposite force. Okay, again, now that you're tilting it, again, let me make mg a little bigger. Again, guess what bam that is? Guess what bam that is? Guess what boom that yellow little distance is? Guess what we'd be calling that? Let's say, let's pop this out to Alexandro. Okay, that's the lever arm distance. Okay, take that force in newtons, that's just the weight of the refrigerator in newtons. Multiply by that distance in meters, guess what that produces? Guess what that be making? Let's say let's pop this out to Adam. That's a torque. That torque is going to make that refrigerator rotate, huh? Now, again, when it's in this position, boom. Again, that force is the same as that force. Okay, it's just the weight of the refrigerator. But again, gang, but won't that little yellow distance there? That little yellow distance there is the blank distance. Any idea what pops out to Sean? Yeah, that's the lever arm distance, huh? Again, that force times that little distance, again, will tend to want to make it rotate. Okay, does this torque, the torque acting on the refrigerator when it's in this position, does it tend to want to make it, again, rotate clockwise? Or would it tend to want to make it rotate counterclockwise? Okay, this torque, can you see, this is hard for some kids, to see, again, which way the torque is going to make it rotate. Take that force times that distance in meters, that force in newtons times that distance in meters, you're finding out how many newton meters of torque acting on the refrigerator. But again, torques have a direction, along with a magnitude. Again, is the direction of the torque going to be this way, or this way, counterclockwise? What do you be be thinking? Do you see it? Let's pop this out to Catherine.
Clockwise.
Hey, muy bien, gang. That would tend to make it want to rotate clockwise. Gang, how about the torque acting on this refrigerator? Would it tend to want to make it rotate counterclockwise or clockwise also? What do you be thinking? Let's throw this one out to, what do we go with Gus?
I believe clockwise.
Muy bien, gang. The counterclockwise, the opposite direction, huh? That's what he thought. He's got the directions messed up. So again, what do I make it want to come and kind of sit back down again? On its that side, whereas this one, gang, is going to tip it over. So again, this one produces a torque, which is going to act counterclockwise. This one's going to be a clockwise torque. Gang, which torque is larger? Boom or boom? The torque over here, gang, acting on the middle refrigerator, or the torque acting on the refrigerator on the end? Which is the larger torque? And therefore would produce a greater acceleration. Any idea? Let's throw this one out to, what would you be saying? Anna?
I don't know.
Which one?
I don't know.
Oh, not real sure, that's okay. Want to dial up friend? Okay, don't want to dial friend, that's fine. What say you? Let's pop this out to, I'll dial one for you. What do you be thinking? Let's pop this out to Devin. Hey, muy bien. Hey, why is it the one on the right? Bigger torque, more twisting force. What do you be thinking? Let's pop this out to F. Hey, gang, the forces are the same, but isn't that a bigger lever arm distance? Gang, torque isn't just force, it's force times the lever arm distance. Gang, make either of those ideas bigger, gang, you make a bigger torque, a bigger twisting force. And therefore, gain more rotational acceleration.
So the force is equal to mg.
Right, in this case, the force is mg.
Okay.
That's true. So it's just the weight of the refrigerator, mg. Okay, gang. So, gang, really, the new thing now in this unit is if you want to make anything rotate, gang, the doorknob. If you want to rotate the doorknob, that takes a guess what? Let's say let's pop this out to Alexandra.
Larger distance.
What was that?
A larger distance.
Did you say something that begins with a T, ends with torque?
Torque.
A torque, gang, that takes a torque, a twisting force. Gang, you want to turn that faucet on. That's going to, what does that take? Let's pop this out to a Jace.
Torque.
Gang, that takes a torque. Gang, you want to, gang, by the way, gang, you want to remove that nut or tighten it down. Gang, that takes a guess what? To twist that thing off or twist it back on. What do you be thinking? Let's pop this one out to Anna. Yeah, as a matter of fact, just to see how mechanically inclined Anna is. Is he taking that nut off or putting it on? Because I know he's kind of like Mason. He knew all this. He knew most of the stuff I was asking. He's a home flipper. Did you know that? Mason Tackmeyer flips homes. You ever watch that on a DIY, do-it-yourself network? Home and Garden Television, they do that sometimes. So you did that, Troy, watching those shows?
Yeah, I don't have that channel.
Oh, you don't? Again, now I get those channels. Again, I enjoy all that stuff. When I was younger, I watched it all the time. Anna, you be annoying? Are you a home flipper?
Taking it off.
Gang, taking it off. Gang, what was the nice little saying we have for taking it off? Or putting it on? Any idea? Hey, lefty loosey, righty tighty. So there you go. Okay, if you didn't know that. Okay, well, which way do I turn? It's not coming. You think you're tightening it down. Okay, you want to take it off? Okay, lefty, go to the left. Lefty loosey. Okay, go this way. Righty, righty tighty. That's the saying. Gang, that's almost always said. Now, gang, some of them are reverse threads. Gang, where do you see reverse threads where it's the opposite? You're trying to do it the way almost everything works, and then snap it off because it was really reversed. Anybody who's changed out a toilet knows this. Put in a whole new toilet. Ever do that now? Yeah, I did it several times. Jason?
Yeah.
You've done it?